So this is another bonus example if you're looking for some extra practice. You should certainly give it a try on your own first before you check for the solutions. But if you want some extra practice, this is not a bad one to try out. There's a sinusoidal wave traveling in the positive x direction, so the wave speed v is to the right. The amplitude is 15 centimeters from the equilibrium to a crest. The wavelength from crest to crest, that's 40 centimeters. And the frequency of the oscillation is 8 hertz. The vertical position of an element of the medium at t equals 0, so if this is a snapshot at t equals 0, is 7.5 centimeters. So right here, that's 7.5 centimeters. So that's the height at x equals 0 and t equals 0. Part A, find the angular wave number, the period, the angular frequency, and the wave speed. So let's start with wave number k. So for part A, our wave number k is 2 pi over lambda, 2 pi over 0.40 meters. You could leave it in centimeters, but traditionally we stick with meters. So 2 pi over 0.4 gives us 15.7 radians per meter. Find the period t. We know the frequency, so period's pretty easy. Period is 1 over frequency. So that's 0.125 seconds. Next, find the angular frequency. 2 ways to do that. You can say omega is equal to 2 pi f, or omega is 2 pi over t. Both will give the same answer, which is 50.3 radians per second. And last, find the wave speed. Wave speed is a symbol of v. Remember, transverse velocity has a subscript of t on it. Wave speed is just v. 2 ways to find that. You can do f lambda or omega over k. I'll do omega over k. And we get for a wave speed 3.20 meters per second. It's part A finished. Part B, find the phase constant phi naught and write a general expression for the wave function. Wave function is also the equation of motion, so wave function means write the equation for D with the numbers that you know. Should be getting a little bit familiar with finding phase constant now. We'll put in the things that we know and we'll solve for our phi naught. I think I'll grab a fresh sheet of paper just so this one doesn't get too crowded. Okay, so to start to find our phase constant phi naught, let's write down our general wave function with all symbols. So d of x and t equals a times the sine of kx minus omega t plus phi naught. I'm trying to find phi naught, so let's see, what do we know? We know that if x is 0 and t is 0, d is 7.5 centimeters. So let's fill in those things. The amplitude is 15 centimeters times the sine of k, which I already forgot, 15.7, times 0, minus omega, which I also forgot, 50.3, plus phi naught. So 7.5 divided by 15 gives us 0.5. Equals sine of phi naught. So that 0 leaves us with phi naught. It means that phi naught is the inverse sine of 0.5. Okay, inverse sine of 0.5. You probably know where we're going with this. We have to be very careful with what we're finding, and how are we going to be careful? Okay. So if you grab your calculator and you do the inverse sine of 0.5, now that I have my calculator handy, we can even try it. So inverse sine of 0.5, your calculator tells you 0.523. That's this angle right here. So the sine of 0.523 equals 0.5. You can try that if you want. 0.5. A little bit of rounding, but close enough. But this isn't the only answer. So that's our answer in the first quadrant. There's also an answer in the second quadrant, because that's how sine functions work. This angle over here has the same value of sine. So this angle would be 0.523. This angle right here would be pi minus 0.523. So pi minus 0.523, that's 2.62. So the sine of 2.62 is also 0.5. You can try that if you want. It's also 0.5. So now the question is, which one? If you want to find which one, you have to test against the velocity, which gives the right velocity. So let's write down our velocity equation. Let's plug in both of these phase constants, and let's see if our velocity is positive or negative, and let's see what our velocity is supposed to be. Okay, so let's do the velocity test. So our velocity equation, our transverse velocity of x and t, is the derivative of our height equation. So that equation is minus a omega cosine kx minus omega t plus phi naught. At 0 and 0, these two terms are 0. So if our phase angle is 0.523, our phase constant is 0.523, that gives us a transverse velocity at x equals 0 and t equals 0 of minus a times omega times cosine of 0.523. That turns out to be negative. So the cosine part would be a positive, positive times a negative would be a negative. Negative velocity means that bit of string is moving down. Okay, so it says if our phase constant is 0.523, this little piece of string is moving downwards. What if our phase constant were 2.62? That would give us a transverse velocity, which is positive. So the cosine of 2.62 would be negative. The negative times the negative would be positive, which would tell us that that little piece of string we're moving up. Okay, I feel as though we're still stuck with the question, because right here when we're reading the problem, it doesn't say if it's moving up or down. So for the moment, we're still stuck with the question, which one? Let's go back to our picture. So here's our wave. Remember, what we're trying to figure out right now, to get our correct phase constant, we need to know, is that little piece of string, is it moving down or is it moving up? Remember, that's a question we asked back when we started traveling waves and we opened up the simulation and we looked at what the little dot was doing. We have to reproduce that idea. If we see that it's moving down, then this is the right phase constant. If it's moving up, then this is the right phase constant. If you're not quite sure how to sort out if it's moving up or down, why don't we draw that wave a little tiny bit of time later on? So our wave is moving to the right, so over time, a little bit of time later, our wave kind of moves over to here. Right? It shifts to the right a little bit after a little bit of time. So we know that's what happens a little bit of time later. So what happened to this point on the string? that point on the string moved down. So point at x equals 0 at time t equals 0 moves down. That tells us that our transverse velocity at 0 and 0 has to be negative. Okay, now we've sorted out which one to pick. The bit of string moves down, so this has to be our phase constant. Okay, now we can finish up our question. So we found the phase constant, 0.523. Write the wave function. That means write the equation for the wave with all the numbers that we know plugged in there. So to finish up, so our phase constant is 0.523, and we know that because we've tested it. So then d of x and t, the height of the wave at any position at any time, is the amplitude, 15 centimeters. Of course, you can put that in meters if you prefer, times the sine of k, wave number, 15 times x, minus omega, the angular frequency, 50.3 times t, plus our phase constant, 0.523. So this equation describes this wave at all positions and all times. So that finishes up our bonus example. We've got one more slide to do in the proper part of the lecture, and then we'll be done.